Hello everyone, my name is Chris Sondagar and today I'll explain an important topic from fiber optic communication, losses in fiber optic communication. In this video, we will understand what causes signal degradation in optical fibers, how different type of losses occur and how we can minimize them to achieve efficient communication. To begin with, let's understand the basics. First of all, what is light? Light is an electromagnetic wave generally with a frequency range of 400 to 800 terahertz. Because of this extremely high frequency, light provides very large bandwidth, allowing huge amount of information to be transmitted. Another advantage of using light is that it is completely immune to electromagnetic interference, making fiber systems far more reliable than copper cables. Now, what exactly is a fiber optic cable? It is a very thin strand of a glass or plastic built with three layers: the core, the cladding, and the outer jacket. The core carries the light, and the cladding surrounds it uh, to trap the light inside through the principle of total internal reflection. You can imagine the core as a light pipe where light enters, reflects repeatedly, and reaches the other end with minimal loss. For this to work efficiently, the light must enter the fiber within a particular acceptance angle. There are two main categories of fibers: single mode fibers, which allows only one straight path of light, and multi mode fibers, which allows many paths or modes of light. The difference becomes important later because it directly affects dispersion in optical fibers. As light travels through the fiber, it experiences different kind of losses. The main types are absorption loss, scattering loss, bending loss, and dispersion. Each of these reduces the strength or quality of the signal in a different way. Let's look at them one by one. Absorption low. Absorption loss occurs when light energy inside the fiber is converted into heat. It mainly happens due to the impurities in the glass, such as hydroxyl ions and metallic ions. These impurities absorbs part of optical power, resulting in attenuation. In simple words, absorption loss happens when the material of the fiber absorbs the light. Now next, scattering loss. Next is scattering loss, primarily Rayleigh scattering. This occurs due to tiny microscopic irregularities in the fiberglass structure. These variations scatter the light in random direction instead of allowing it to travel straight. This loss is stronger at shorter wavelengths, which is why optical communication prefers wavelengths like 1310 nanometer or 1550 nanometer, where scattering is minimal. The graph for these we will see in second last slide. Rayleigh scattering is also responsible for why the sky looks blue. Shorter wavelengths scatter more. Bending loss. Bending loss occurs when the fiber is bent beyond its critical radius. There are two types: macro bending, which is caused by visible bends or loop, and micro bending, which results from tiny pressure points or imperfections. When the fiber bends, the light no longer reflects properly inside the core and leaks into the cladding, causing signal loss. This is why careful installation and proper handling of fiber are very important. Dispersion. Dispersion is slightly different from attenuation. While attenuation reduces power, dispersion distorts the shape of the signal. In optical system, information is transmitted as pulses. If these pulses spread out too much, they start to overlap and cause errors. Dispersion limit both maximum data rate and transmission distance. The first type of modal dispersion, which occurs in multi-mode fibers. Since different light rays take different paths, some straight, some zigzag, they reach at the end at different time, which causes the output pulses to be wider than the input pulse. Modal dispersion is major limitation in multi-mode communication over long distances. Now some advanced dispersion types. The next is chromatic dispersion. Light sources such as LEDs and lasers do not emit a single wavelength. They emit a small range of wavelengths. Each wavelength uh, travel at a slightly different speed in fiber, causing the pulse to spread out over time. This effect becomes slightly in long distance communication. Another advanced dispersion type is polarization mode dispersion or PMD, which mainly affects single mode fiber. Light can have two polarization states. Ideally, both should travel at the same speed, but due to tiny imperfection or asymmetry in fiber, each connect polarization travels differently. The difference in arrival time leads to pulse broadening, which is critical in very high networks. Attenuation versus wavelength. This chart shows how attenuation varies with wavelength. We can see in the chart two losses window around 1310 and 1550 nanometer, which is why most optical system operates in these ranges. At short wavelength, scattering dominates, while at longer wavelength, absorption increases. So the goal is to operate where total loss is minimum. To reduce fiber loss, several techniques are used. Use high quality and high purity glass materialized to minimize absorption. Avoid sharp bands during installation. Choose the optimal wavelength windows. Use single mode fibers for long distance. Use laser sounds with narrow spectral width to reduce chromatic dispersion. By following these methods, we can keep signal quality high even for long distances. So, in summary, optical fiber offers high bandwidth and low interference, but the signal still experiences losses as it travels. The major losses are absorption, scattering, bending, and dispersion. Understanding these losses is essential for designing efficient communication system. Thank you for watching.